Welcome back, everyone, to Nirvana stage. Next, we have Natale Vinto and Rafael Cardona. And here is what we know about them. Natale is a software engineer with more than 10 years of expertise on IT and ICT technologies and consolidated background on telecommunications and Linux operating systems. Computer engineer, DevOps enthusiast, and FOSS contributor, he is currently working as developer advocate for OpenShift at Red Hat. Now, Rafael is a seasoned senior solutions architect based in the Netherlands. He is specialized in cloud infrastructure and high-performance computing systems. Rafael has a relevant expertise as systems engineer in Linux operating systems, 5 years work experience in banking, and more than 14 years in the IT sector. And today, they're going to let us know what building supercomputers using Kubernetes and OpenHPC is like. So, word to you, guys.
Hello, everyone. Welcome to the session of building supercomputers using Kubernetes and OpenHPC. First of all, thank you for having me here today. The goal of this session is to share our experience in the HPC and cloud industry and give an opinion of how could be the best, how we can use the best of these technologies in order to integrate and create more powerful computational systems, so-called supercomputers. I look forward that you enjoy this presentation. Next. As I mentioned before, my name is Rafael Cardona. I'm a cloud solution architect based in the Netherlands. I work for Red Hat. Of course, it's not a coincidence. As I am an open source enthusiast, I started my IT career with working with Unix and Linux systems around 15, 14 years ago, which has been definitely one of the best decisions of my life. All in all, it has led me to the position I am today, working closely with customers, empowering them to bring their applications into the cloud, specifically into enterprise Kubernetes. The most relevant projects I'm currently involved is regarding 5G core and bringing that into Red Hat OpenShift. Then I got the pleasure to introduce my co-processor is Natale Vinto.
Hi everyone, my name is Natale Vinto. I'm developer advocate at Red Hat. So thanks for joining us today. Thanks there for the introduction. We are very excited to be here at BuildStack, first time for us. We hope to have fun with us, with you, and really looking forward to see you on site for our next edition on site. But today we're going to talk about Kubernetes and supercomputer. And I give my the voice again to my colleague. If you like to follow us on Twitter, this is my handle, Natale Vinto. Please use the hashtag BuildStuffConf. And if you like Kubernetes and OpenShift. So to you.
Thank you very much, Natale. Okay, I end very good. Okay, without further delays, let's jump into the agenda. I will start by defining what a supercomputer is. Thereafter, I will explain what OpenHPC is, how its ecosystem of projects work. To finish this part of the presentation, I will explain some technical details of a typical HPC deployment. In the second part of the presentation, Natale will give you an overview about what Kubernetes is and will dip into how its scheduler mechanism work. It is worth to mention that the first two parts are key to be able to digest the third part, which refers to the proposed solution for the integration. And to close the end of the presentation, I will mention some projects in which I have been involved either directly or I have the in-depth knowledge of what is that about. And the conditions that they involve HPC and Kubernetes. So, next. Okay, what is a supercomputer? What a niche word. Without that, its definition has to.
Hey, before this, Rafa, we're gonna have some questions.
That's true. Excuses, Natale, but I like you to do this part as well.
All right, all right. So we are at Build Stuff here. I know you rock and code. We all rock and code. So we want to know a little bit about you. So who you are? You are a Rockstar developer. You're a Rockstar ops person. Who you are? So please vote to this poll you see here. And I hope somebody can share the link also in the chat so we can have this vote for you. So the first link is the slide deck. So you can follow with us all the links in the slide deck. And then the second link we're going to share in the chat is the link of the poll. So let me share with you also this QR code. So if you have any mobile here, you can follow this QR code. And let me share also the link with you in the chat over here. Here we go. So you can vote in this poll over here. And let me share also, if you would like, also in the Slack channel, if you want to vote who you are, if you are a Rockstar, and we can follow this. We can follow this. So if there is anyone voting here, oh, we have 2 developers. Come on, no Rockstar yet. We give a little minutes for people to vote here. So we want to know if you are a developer, a sysadmin, IT architect, IT man. Oh yeah, a Rockstar. Great to have some Rockstar over here. So we have some diverse audience, right? We have some developers, sysadmin. We have some Rockstar, which is really great. We leave some seconds yet for people to vote over here, and you will see in the voting here that all the results are coming. So we have 10 voted on the moment. All the other votants, I guess they are coming up. So let's leave a little bit this running. It looks like we have more developer, Rafa. So we have to talk with developer and Rockstar today.
That's a great audience.
Let's do this. Let's do. So thanks everyone for voting. Please keep voting. We will share the result at the end, so we will discuss about it, and we'll continue here in the presentation. So I'll leave again the words to Rafa for this great topic of today.
Thank you very much, Natale. Okay, coming back to the concept of a supercomputer. During my years presenting what an HPC system is, it's turned to be the most difficult concept to define because it's such a global world that many people have many different concepts. That's why I would like to clarify a common ground for all of us, so we can really find the best approach to integrate the best of both worlds. As I said, the word supercomputer is definitely in the podium of the most opinionated in the IT industry. However, we can all agree that a supercomputer is a system that operates at the highest standard of level of performance. In order to know what the highest level of performance is for a system, then we should start by understanding how that performance is commonly measured. And it is done by counting the flops, the floating point operations per second. If I'm not mistaken, the last measurement was done in June this year, and a computer called Fugaku, a Japanese computer, topped the list with more than 400 petaflops. In the second place comes Summit, and that followed by Sierra. They closed the top 3 supercomputer. Both Summit and Sierra are IBM systems. Further, all 3 run on Red Hat Enterprise Linux, while Fugaku use Fujitsu microprocessors. Summit and Sierra use both IBM power as expected. The question is now, how those systems manage to execute that amount of operations? Well, the answer is quite straightforward. It is all about executing tasks simultaneously. Now we come for a more complete definition, and that is that a supercomputer is able to execute a huge amount of computational tasks in parallel. Serial processing is definitely not a task you would like to give a supercomputer. It will do the job, but definitely you will be wasting millions and millions of euros if you give a serial task to a supercomputer. Can you do enter, Natale, please? Okay, that is a division I made, the part of defining a system depending on the task they process and the type of processing it's performed. So we want to focus in parallel. And Natalie, do enter again, please. We're going to talk about the architectural element of a supercomputer. We start by processors. More than being a specialized design for this type of operations, it is more about how they are collocated and configured to run those operations in parallel. Then we come to a very important differentiator between supercomputers, and that is where are those microprocessors placed? When they are too close, the heat density plays a big degrading role. So the solution for that is to set them apart. It looks like a simple solution, but it's actually very complex at the end. To separate processor, to set them apart in a minimal distance can change greatly how the performance of a computation is. Then we have two general architectural approaches. One is called cluster, one is called grid. Cluster refers to the nearest co-location of processors, while grid focus in or target to setting them as far as possible without losing the performance that you want to achieve with the computation. The supercomputer family is big and diverse. For the sake of time and following the goal of the integration, I will focus on open source software and on commodity hardware. However, it is worth to mention that the mainframe system and other non-distributable systems are other type of supercomputers. Distributed and tiled couple architectural approaches bring a new designed element. If you do enter, please, Natale. At the processor unit are further apart. A high throughput interconnect has to be placed in order to keep the desired performance. Just as when the processors are close as they could communicate over an electronic buffer like in a blade. So interconnect and high efficient storage are key to keep the performance of computational operations. The parallelism of computational operations is not trivial. It requires an ecosystem of highly integrated components. Among of them are the provisioner, the resource manager, task manager, APIs, orchestrator, runtime excuses. The provisioner cares that every node in the grid is properly deployed. The resource manager is in charge of welcome or evicting the resources in the grid, the cluster. The task manager evaluate and authorize the feasibility of the task. The API is the interface to the grid, to the cluster. The orchestrators ensures that the tasks are aware of each other and cares that the outputs are completely unreliable. The runtime are basically the libraries installed on the worker nodes where the application performs the computations. There are a good number of commercial software. However, the core development, a substantial majority of the APC system have taken place in the open source world. If you do enter, Natale, please. Okay. The name you can read in the slide refers to some of those software packages, being XCAT, the most popular automation tool in this space. It could also be used as a configuration manager and even support the provisioner in the deployment of clusters. I found XCAT very useful. I use it extensively when I was working with IBM LSF, and without doubt, it's like the rock star in the open HPC environment. Slurm is a very, very intelligent piece of software. It stands for Simple Linux Utility for Resource Management. However, it is more than that. It is also a task manager and and control the scheduling of the tasks. So we can call that a very intelligent scheduler. And another important piece of software here would be Waterwolf is de facto provisioner, while Lustre is the parallel file system, and all this bring me to the next slide, Natale. What is OpenHPC? Some people tend to confuse and assume that OpenHPC is a product. In reality, it is not a product. OpenHPC is a venture of open source projects that aim to provide a set of privileged software packages and documentation designing to maintain HPC system. It provides a common platform to the HPC community that works across multiple segments and on which end users can collaborate and innovate. It basically looks to simplify the complexity of installation, configuration, and ongoing maintenance of a cluster software stack. You do enter, Natale, please. Although OpenHPC was initiated by Intel, nowadays there's a significant number of project members. There you can see big names in the HPC world like Cray, Red Hat, HP, Lawrence Livermore, that is basically IBM. The takeaway with OpenHPC is it is a Linux Foundation venture. It's a purely community effort. There's no commercial initiative involved. The primary output is a standard delivery model of all mini project inside the venture, and the base of all improvement are redirected for the R&D initiative within the companies who are involved. This is a typical deployment of OpenHPC. The best way to know how all these open source packages work together is by seeing a standard deployment like here. As you see at the master, you will see the condensated the overlay and the POP network configuration, the identity management, system management, configuration, inventory, APIs, the task manager, the resource manager. A simple use case here would be to place a job request into the master. The task manager will analyze if the cluster is able to carry on the job. It will look at the pool of resources. It will decide where to place that job. And then we decide with the scheduler where it should be placed. Then it is query into the orchestrator. The orchestrator will analyze if that job will encompass more or the amount of jobs that will run together, and will track of that. The job is deployed to one of the workers. The worker will access the storage through a high performance storage layer, which in this case is supplied by Lustre. And then when the computation is done, the results are submitted to the master, and then after the runtime complete the job, the results are submitted to the master, and then the results are gathered and given back to the user request. Okay, next, next, Natale. Are you on time? Yeah, I'm on time. It's all yours.
All right. Thanks, Rafa, for this introduction for the topic we have to talk today. So let me share again my screen over here. I hope you can all see it. Here we go. So let's talk about Kubernetes now, because we want to mix this word of supercomputer with Kubernetes. But for people that doesn't know good Kubernetes, let's deep dive a little bit about it. So Kubernetes is Greek for Hellman. This is the Kubernetes word in Greek. It means a helmsman or governor, from Latin also gubernator. It's a container orchestrator. So the job of Kubernetes is orchestrating containers. and support multiple cloud or bare metals environments. So you can run Kubernetes on public cloud, private cloud, your data center, even your Raspberry Pi works run everywhere. It is de facto common fabric for any modern app workloads. And not only, and that's why we were talking about this today with Rafa. Let's see a little bit the components of Kubernetes. Now we understood Kubernetes is a container orchestrator. Let's deep dive a little bit. So Kubernetes is component basically of a control plane, which is controlling a cluster, and some node, which are the data plane, the worker plane, as you want to call it. So Kubernetes is a container orchestration platform, and it's a cluster. This cluster is component of some master nodes with the control plane and some nodes, the worker nodes. So your application, your containers run in such nodes. But they're all the job that the control plane makes to ensure your workload are running properly in this cluster, in this environment. And we will talk about them in specifically. The thing to remember is that Kubernetes is a component of multiple control plane objects, which are the API server. So all the Kubernetes logic is API driven. So there is an API server responding for all requests that you have in your cluster. And then we have the control manager. So the control manager is the one that ensuring that everything is fine with the declaration in the cluster. This is a declarative platform. You can declare how you want your platform to behave in according to the infrastructure as a code paradigm. And there is also a database for this. So all your settings will go to this database, which is etcd. It's a key value distributed database is used by this cluster. And most important, we have the scheduler. So the scheduler is the one in charge of placing your workloads in the best suitable nodes. And the discussion of today is to understand how we can fit the Kubernetes scheduler with the supercomputer, also supercomputer paradigm. So merge and join these two words. Let's then you have as we discussed the node. So let's talk about a little bit the Kubernetes object. Kubernetes works with some workloads which are organized in pods. The pod is the smallest deployable unit of computing inside this cluster. So you may know already a container. In the previous talk, we were talking about microservices. Typically, those microservices are bundled in container. So you basically run your microservice inside a container. And Kubernetes itself doesn't talk directly to a container. It talks to a meta layer, which is the pod. The pod is just a representation of container, and specifically one of more containers. So you can have one pod with one container, and this is the most common use case. And then you have one pod with multiple containers. This is another use case that can be useful. But in general, Kubernetes will orchestrate the pod, not the container. And who decide who is the where to put the node, where to put the pods in the right node is the Kubernetes scheduler, the component that we saw before. So the scheduler is responsible for finding the best node for the pod to run on. So the scheduler is a component of a control plane that take the pod and place in the best nodes. In order to understand which is the best node, there is an algorithm that the scheduler apply. In particular, the component to do this is called inside Kubernetes called Kubescheduler. And this is in charge of finding the feasible node in the glossary of the Kubernetes architecture. A feasible node is a node that met all requirements to run the pod. Because when you want to start your microservice, your application, and you need some RAM, you need some CPU, you need some storage, so you declare that you ask to the platform, hey, I want this RAM, I want this CPU, and the platform is in charge to finding the best node that can serve your request. In order to do this, the platform has a scoring system. This scoring system is made according to some policies that the scheduler has. So the node with the highest score get the pod, because in general, the most free, the most available node hosts the workloads. And this helps also Kubernetes distribute the load on your cluster. In details, what happens under the hood is that you have two phases in the scheduling cycle. One is the sorting. So basically, you filter the node, the resources that you have in your cluster, and then you apply the scoring algorithm. Once the scoring algorithm decided that the node is the most suitable, you basically do the binding. So you bind the pod to a node. So if you remember, we have filtering, then scoring, and then binding. Those are the three phases in which Kubernetes decide where to place your application, where to place your container, your microservices in the cluster. The scheduler is responsible for finding the best node, and how to do it. It does it with policies. So this works with policies, and let's see this in action. So this is a typical Kubernetes cluster, right? We have some master nodes. So if you remember, this is the control plane, and then we have some worker nodes. So the node that hosts your application. Let's do a common use case. Let's do a common use case, which is can be, I want to deploy this Tomcat app, and I want 4 replicas. So I want 4 instances of my Tomcat app. So I ask to the platform, and specifically to the control plane, hey, place 4 Tomcat instances, please, for me. And the scheduler will take this request and place the Tomcat app, your microservice, in this case, this Tomcat app, in the most suitable node according to the scoring system. What happens when a pod fails? And here comes the scheduler benefits. So the controller retrieve that there is one failing pod, and the scheduler find another suitable node for that pod. So if you remember, if you see, the Tomcat app has been moved from the failing part to the other node, just because this node maybe it has more RAM, more resources. What happens when a full node fails? The controller get this info. So say the cluster now has a lower number of nodes. So the scheduler will find another node. Also, the scheduler will find out if there is any new nodes where to run the application, and can place your Tomcat app over there. So you have seen how it works under the hood. If you have any failing app, the application, the pod, got moved by the scheduler automatically, even failing node or failing pod. This happens thanks to the Kubernetes scheduler that work with policies and profile. Those policies can be used to specify predicates. So if you want to customize this behavior, if you like to modifies this behavior, if you want to make some priority on some storage, priority on some nodes, you can modify the predicates. Pretty easy. It's a JSON file that you can modify, and you can also get some priority to help the kube scheduler run the filter and scoring system for you. I give again the voice to Rafa, which is going to explain us how we can mix this world of Kubernetes and HPC, the supercomputer and Kubernetes all together.
Okay, perfect. Kubernetes is doing a workload and resource management just as HPC does. In many ways, it shares a lot of functionalities with traditional HPC workload managers. The main differences are that the workload type they focus on, while HPC workload managers are focused on running distributed memory jobs, MPIs, and support high throughput scenarios. Kubernetes is more is focused or is built for orchestrating containerized microservice application. When you see those two boys, OpenHPC, let's call it the ecosystem HPC, and what is focused on. And you see in the right side, you see Kubernetes and what they focus on. They do similar jobs, but their targets are different. However, the expertise and high performance of one can be used in the other. I have seen some initiatives trying to bring the methodologies of Kubernetes into HPC, but it has been definitely not the right approach. For the ones who know HPC, how it's behaved, most of the things are legacy. They were wonderful. The performance is amazing. The throughput is without match, and you can run amazing computational tasks on there, but it's not flexible. You have to in most of the cases you have to pre-deploy the clusters, pre-configure before you can do any calculations on them. Kubernetes is completely different. Kubernetes, of course, you have to have the worker nodes and the control plane already in place, but the deployment of the application pods, it will be dynamically, and it can be even done automatically. The system is self-healing, self-managed, so it's a completely different approach. So what I have seen in the community, they abandon the approach of integrating Kubernetes features into HPC, but bring in the other way around, bring the good things of HPC into Kubernetes, and it has turned to be very interesting. The four element I put that the little guy, the HPC guy, put into his board are the one who make the difference for being able to run those HPC workloads in a cloudified environment. Let's call it like that. There is a way through, and the way through is paying off in the way that we are integrating currently HPC workloads in Kubernetes. But shared memory is targeted exclusively to be able to perform MPI to execute MPI tasks. For that, we need to enable a high throughput network layer. SDN, the native SDN that Kubernetes have, is definitely not a match. So that's the reason that certain initiatives have been taking place in the last years in Kubernetes. Now we got a SROIV operator who allow us to make usage of that single root devices and make them available for the pods. You got also the CPU manager who allow you to understand what the architecture of the CPUs who are present in the workers, and the topology manager who allow the cluster to be aware where the different resources of the cluster resides. Okay, this is a solution I have been working on. It's not battle-proof, but it does the job. The solution I have been working, as I said, is based on enabling high-speed interconnect into Kubernetes. It is done by configuring RDMA, which is a protocol that allows direct memory access from the memory from one computer into another computer without involving the kernel. It allows massive throughput, low latency, as I said, perfect for a massive jobs. The overlay network is it's attached network is created to maintain containers group together into a subnetwork. So containers are physically located in different host machines, but they share the same subnet address space and the same SDN. As I mentioned, RDMA for the containers was done to be able to map the VF devices into the application's container. What is my conclusion about this solution? It's not complete. It's run the job, but we don't make usage of all HPC features that we would like. Ideally, it should combine both Kubernetes and the HPC workload management system to fully meet the HPC requirements. Kubernetes shall be used for managing HPC containers along with all required services. Inside the containers, not just engineering can be run, but also the capability to either plug into an existing HPC cluster or run an entire HPC resource manager installation. So it needs to be provided, like in this case, Slurm. In that way, it is needed to provide the compatibility to the engineering applications and could be exploited to extend the batch scheduling capabilities. At the same time, our whole deployment can be operated in all Kubernetes enabled environment with advantage of standardized container orchestration. I mentioned that shared memory topology, HPC storage, and CPU architecture is the meeting points, but we forgot in the industry, in the open source, how to really make usage of the scheduling, the powerful scheduling of HPC into Kubernetes. And well, last year I had the pleasure to get to know that IBM was working in this, and they create a solution that, even though it's not perfect, is going in the right direction. You do enter, Natale. Yeah, this is about the LSFI connector, or IBM Load Sharing Facility Connector. This solution is a bit more innovative from my point of view, because it integrates the scheduler of both systems, allowing the provisioning of Kubernetes scheduling of the worker nodes. IBM Spectrum LFS connector for Kubernetes uses the core IBM Spectrum LFS, as I mentioned. It is integrated into Kubernetes itself. The LFS connector for Kubernetes combine the Kubernetes API functionality with the resource sharing and load balancing technology of LFS. The LFS scheduler components are packaged into containers, and Helm chart is provided to deploy into Kubernetes environment. Users submit a workload into Kubernetes API via kubectl to get the LSF scheduler, to be aware of the pod, the scheduler name, field map test. Otherwise, the pod will be scheduled by default scheduler. Scheduler directives can be specified using annotations in the pod. In order to be aware of the pod node, LFS scheduler uses a driver that listens to the Kubernetes API server and translate pod request into LFS scheduler. When the LSF scheduler makes a policy decision on where to schedule the pod, the driver binds the pod into a specific node. Then the Kubernetes will execute and manage the pod lifecycle on a target node in the normal fashion. The LFS scheduler also supports submitted job from native subcommand, which are mapped into the Kubernetes pod and executed by Kubernetes as well. In this way, it's very consistent. However, there are some drawbacks also in this. Many of the features that LFS don't work. For example, the job resizing. Kubernetes is not able to resize the batch job the way that LSF does, but that's on the way. And LSF data manager, who allowed you to collocate data close to the execution node, is also not possible with the current setup. And yeah, the polls cannot be terminated, be killed, which is a very important command in the LSF. The last part I would like to share with you is the how can I say, my favorite projects. Not all of them are open source, but I have been involved directly or indirectly with each of them, particularly the IBM Cloud Pack, which is open source, and with the Netherlands Health Institute regarding the computation of analysis of computation and analysis of the pulsations of the heart in children.
We have 4 minutes left. 4 minutes left.
Okay, and the way that HPC and Kubernetes can combine together to bring good information to our society, how we can maximize certain things, energy, how to test different medicines, is really amazing. So I invite you to click in the links that you see that you will provide the Zoom, and you will be amazed for the thing you can do with HPC and Kubernetes together. Well, I think time has come to us. Thank you very much for your attention, and I leave it to Natalia, and then we can go to the Q&A.
Thanks, Rafa. So you find all the links for the Supercomputer project in the deck. I shared it in the chat. So we have another poll over here. So if you like, we want to know if you are for supercomputer, hybrid cloud, are you super or hybrid? So please vote. I hope you get the link in the chat soon. Otherwise, I can start sharing it. Please vote also here. You have the QR code. You have the link over here, and you should get the link also in the chat very soon. Let me do for you if we can have it there. All right, so I share the second link in the chat. You can start voting here. We want to know if you are super or hybrid. So this is our second poll over here. If you are for supercomputer or only, if you are for Kubernetes only, or if you are for super hybrid, like we say today, if you would like to have the both word with the two projects that Rafa shared with us. So there are some votes coming, and we will share. We are in shortage of time, so we will share those polls after that. So please keep voting. We will share with you the result after that. Supercomputer, Kubernetes, or super hybrid. Let's finish this all together. So we have here the poll, and we want to leave us. We want to leave to you also this message. Everything is open source, OpenHPC or Kubernetes, everything is open source, and this is we are part of Red Hat, and this is basically also our mantra, that everything is open source. So the project is open, and we also want to leave you some links over here. So this is the link for the OpenHPC community project, open source. This is Kubernetes, the link for Kubernetes. You can get the documentation about how Kubernetes works, the source code. You can start playing with it. Also, we have here some link for from Red Hat. You have here the Dev Nation link. We have talks, documentation, tutorial, video, courses. So feel free to join us. Happy to share this with you. And also this learn.openshift.com. OpenShift is the Kubernetes distribution of Red Hat. Here you have some Karakora online lab that you can do yourself. So you can start learning Kubernetes, learning OpenShift containers from the browser directly. So you can go to this link. You find all the link in the slide. So thank you. Those are our Twitter handle. If you'd like to chat with us, those are the hashtag for today. If you'd like to send a tweet for this, and this is the link to the slide. So thank you very much. And we are, if you'd like to submit some question, we are ready for the question and answer. Thank you.
Brilliant. Thank you, Natalia and Rafael. Just bear with us. We're going to wait a few moments because there's a slight delay in the live feed if we see any questions. But if we won't see any questions, just a friendly reminder, we have a special room to get some Q&A done just with you guys. We can find that on PineTool app where the stage is. There's a little box, chat with the speaker after each session. You click on that, you go in, you can ask some questions. Now, I really love your presentation, guys. How's your first time here in Build Stuff, Digital Edition?
That was great. I like the spirit. I like this enthusiasm that even if it's virtual, it's very, it's something that we feel very much. And I hope for our next time on site with all you. And thank you for everyone attending and joining us today.
Brilliant, Rafael.
For my side, it's really amazing. I've been following what you do, guys, in Build Stuff. The initiatives are fantastic, and as Natale mentioned, it would be great to come back to normal and do it in person. Something that amazed, like I feel I was talking only 5 minutes, and I look at the clock. I was 11:15. I look at the clock again. It's 12:10. I don't know what happened to the time. Like I don't know. Incredible.
Awesome. You know what they say the time flies by when you're having fun. So
yeah.
I guess that was just that. Thank you, guys, and we'll see you later, I guess.
Thank you. Yeah, for sure.
All right.
Thank you. Sure. Bye bye.